Hello everyone, welcome to lecture 7. So today our focus is going to be on splay trees. As we've discussed that binary search tree, in the worst case, the complexity of operations like insert, delete, and search, it amounts to essentially order of n complexity. And therefore, we would like to see how we can improve this. We also discussed that the binary search tree can easily degenerate into something like a linked list. Like for example, when the numbers are coming in increasing order, then as you are inserting the new nodes, you will end up essentially creating a linked list of these nodes. So therefore, if one has to search, then the worst case complexity for the search of any node leads to an order of n complexity. And we also alluded to the fact that in order to bring this down to order of log of n, we need to move in the direction of balancing our binary search tree. So balancing is central to many different varieties of data structures that are founded on the basic invariant of the binary search tree. And we named some of them. So there is the AVL tree, then there is red-black tree, and there is splay trees. So splay trees by far is considered to be most widely used data structure of choice in the last 25 years or so, and therefore we are going to learn how to utilize splay trees in balancing the binary search tree and getting to a much better timing complexity for insert, delete, search, these fundamental operations in relation to the binary search tree. So splay trees are structurally identical to a binary search tree. As I said, they maintain the same invariant, and that invariant is that the left subtree, the keys in the left subtree are all less than the current node, and the keys on the right subtree are greater than the current node. So less than or equal to and greater than. Where to place equal, you obviously have a choice, but traditionally it is considered to be on the left side of a given node. So therefore, this splay tree is a balanced data structure where it's a balanced data structure of choice in real world operations. It's a data structure of choice because it's not very difficult to implement the Splay tree. So what are the key characteristics of a Splay tree? All operations take the order of log of n time on average. So all operations take log n time on average. However, some operations can be very slow. So then what's the point? The point is that although a single operation can be very slow, any sequence of k Splay tree operations starting from an empty tree and never exceeding n items. So never exceeding n items in the tree. This will take order of k log n in the worst case. Okay. So some operations can be very slow. How slow? As we mentioned, it can be of the order of n. So some operations can be slow, but over an application of k Splay tree operations beginning from an empty tree would take k log n in the worst case. And therefore, on average, the time taken becomes order of log n. Okay. So what is the basis for achieving a balanced tree? So balancing of a tree is done through what is called tree rotations. So you will learn about some fundamental rotations that one can use in order to reach a balanced configuration. In fact, the whole beauty about each of these algorithms that we mentioned, AVL, red, black, splay trees, is in relation to exactly how the different schemes are for making the tree rotations. So let's see for splay trees, what are the basic rotations that are possible. Okay. So let's develop an insight for the tree rotation. So here Y is a node and X is another node. So X is a child of Y, and then underneath X you have a whole subtree on the left, and there is a subtree on the right. So let's say this is subtree A and subtree B. And on the right of Y, you have the subtree C. So what can you say about this? So clearly the keys in the subtree A, they're going to be all less than the key of X. Okay. So let's say this X is representing the key that is stored in the node, and Y is likewise representing, although we are calling as node Y, but it is representing the key Y. So here the C is going to be greater than Y. So we can say less than equal to X and greater than equal to Y. And here this is going to be greater than equal to X because it's on the right side, and less than equal to Y because it is on the left side of Y. So what happens when you rotate the tree? So rotate right. So when you rotate it right, it's essentially, it's something like making the rotation about Y. So after the rotation, X will go up. So X goes up and Y comes down. And the left child or the left subtree of X still remains intact. So which is A, the subtree A. And upon the rotation, the right child of Y, which is the subtree C, also stays intact. Now we are reconciling about where to place this whole subtree B. So the subtree B is placed as a left child of Y. And you can see here, the invariants are still maintained. This is less than equal to X. This is greater than equal to X because it's on the right side. This is less than equal to Y, and this is greater than equal to Y. Therefore, upon rotation, you can see that there is no difference that got created. Now one can also see likewise this being the rotation. When you give a left rotation for this tree, you get to the right. When you give the left rotation around X on this right tree, you go to the configuration on the left. So we can put it in this way, that from here, when you rotate left, you obtain this tree on the left hand side. Okay, So this is the basic rotation that we are going to use in coming up with the different rotation strategies for the splay trees. Okay, so let's first lay down how the algorithm may look like. So first of all, let's recall that the splay trees they are going to be balanced trees, but they are not kept perfectly balanced. So now we'll see this point coming through as we are going through some examples. So first, let's look at the basic operations that we are interested in. The first operation we are interested in is the find operation, find or search. And you are finding, again, a key of type key. So because fundamentally splay trees are binary search trees, so you would expect that the find algorithm for the splay tree is going to follow exactly the same algorithm as the binary search tree. So you begin by finding the key, and this is no different from an ordinary binary search tree. So after you have done that, that's when the magic of Splay comes in. So you walk. So after you have done it, then you walk down in the tree to the node with key k. Okay. Or you might reach a dead end or reach a null pointer, because there is this key k is not there in the tree. So let's say X be the node where the search ended, regardless of whether it succeeded or not. Whether succeeded or not. Then what do? Then you splay X up the tree through a sequence of rotations so that X becomes the root. So why is this done? So you can try to conceptualize, like if I draw out some tree like this, and here, suppose you're finding here, and there are many nodes in the tree here. So this may be many levels down, deeply rooted. Now, because you looked for this particular node, there is a likelihood that you might be looking for it again. And that is why this is brought to the root level, so that next time when you are searching for it, you will get it very quickly. And in the process, because of this rotation that you are giving, you would also balance the tree, rather, I would say, semi-balance the tree. So semi-balance the tree in the process. So in other words, for every single action that is done, whether it is finding or inserting or removing, it just gives us an opportunity to rebalance. So this just gives us an opportunity to rebalance the tree. And that rebalancing is done with some very basic sort of heuristic in mind. Or you can say the heuristic literally is just like caches, like in hardware architectures, there are caches. The caches are added to the memory hierarchy just so that they can exploit the locality of reference. So when something is accessed, then there is a likelihood that that another item in the neighborhood would be accessed very soon. Or the same item might be accessed just within a short period of time. So likewise here as well, it tries to exploit the possibility that the same item may be looked for one more time. So this is the scenario. So when the same item is looked up again and again, so this heuristic is going to make it really go faster, because you are bringing that node with multiple rotations to the root level, and therefore when you look it up again, it's going to be super fast. Okay, so that's the basic rationale. So the overall principle of splay trees is to do the right rotation at the right time. Okay, so now what is the right rotation? What is the right time? In order to figure that out, let's explore three cases or three possibilities that would arise for us to think about what kind of rotation to give. Okay, so first possibility is that X is, so when I'm using the term X, you can consider it to be node with the key X, and therefore we are able to conveniently designate the node in that way. So X is the left child of a right child. Or X is the right child of a left child. Okay, so let's see how that may look like. So you have this as the grandparent, and then this is the parent, and you have a subtree, and then you have another subtree here, and then X is here a right child of a left child. So it's a right child of a left child, and you have the subtrees. So let's label them. So this is A, this is B, this is C, and this is D. So what do we do when X is a right child of a left child? So first, what we want to do is we want to give what is called a zig rotation. So zig rotation would rotate this first around the parent. So it will rotate in this direction. And then you would be giving a zag rotation around the grandparent. So zig around the parent. So when you give the zig rotation, how does it look like? So there is a grandparent. So grandparent right subtree remains intact. Okay. Now at this point, as we showed, like when you're giving the left rotation, then X will become the parent and P will become the left child. And we already showed that it does not violate any property, the BST property. And this remains the left child of P. And this remains the right child of X, which is C. And what was the left child of X now becomes the right child of P. So this becomes B. So after giving the zig around P, next you give zag. So zag meaning it's going in the other direction. So this would be rotating around G, the grandparent. So when you do that, what will happen? You have your G. I'm sorry. The G becomes now a right child of X. So X comes up and then G becomes the right child. The right subtree stays intact. P was the left child of X, so that stays intact. And also the subtree A and subtree B for the parent stays intact. But the right child or the right subtree of X now becomes the left subtree of G. So this becomes C. So you can see after making, so this is zag around G, the grandparent. So overall, this scheme of rotation is called zig zag rotation. Now you could imagine that symmetrically, if you were having the X, the node X as the left child of a right child, then the zigzag rotation would have meant you're going first the right rotation, probably we can say clockwise rotation, then followed by anti-clockwise rotation or counterclockwise rotation around the grandparent. So zig zag is essentially pointing out that the two rotations are in opposite direction. And you can see after the zigzag rotation, this tree apparently became a little more balanced than what it was. So there are two effects that you can see. One is that it became semi-balanced. And second, what we find is that X came to the root. So this scheme of zigzag rotation, it brought the node X, you can say, 2 level up. So you can see if this is still not the root level, you will keep doing these kind of rotation until you bring X to the root level. So that series of those series of steps that are taken over a node to bring that to the root level is what is called Splay operation. And we are just learning some of the building blocks of the Splay operation. And there will be 3 basic kind of cases that we will encounter as a step towards splaying a node. So this is the second case. Okay. The second case is, as you would have already guessed, so X is a left child of a left child, or X is a right child of a right child. So we can draw up that case. So let's draw up. So you have G, then P, so grandparent, parent, and X comes as a left child of a left child. So it's a left child of G. On the left, you have a left subtree called A. On the right, you have a right subtree called B. And the right subtree of P is called C. And right subtree of G is called D. Okay. So because this is left child of a left child, you could imagine that just like in the previous case, it was a left child of a right child, and because of which the rotation was zigzag rotation. Now here it's a left child of a left child. So you would have guessed it right that it would be zig rotation as opposed to zigzag rotation. The rotation will be in the same direction. Now the question arises, which rotation to give first, whether to rotate around P first or G first. So this is what you have to remember. The step for this one is rotation around G first, the rotation around the grandparent first. And we'll discuss in a short while why that is so. So this is zig around G. So after you give this rotation, so P comes up. So P comes up, and then G becomes the right child of P, and this subtree D stays intact, and the left child of P was X, that stays intact. The left subtree of X was A, that stays intact. The right subtree of X also likewise stays intact, and then the right subtree of P becomes the left subtree of G. So therefore C comes here. So you might have already noticed that the subtree ordering stays the same. So it is A, B, C, D. Here also you can see A, B, C, D. Previously also you can see A, B, C, D. Doesn't matter whatever rotation you give, the ordering remains the same. And you would have understood why that is so, because we are maintaining the binary search tree property. If there is any interchange of this ordering, that means you would have messed up with the binary search tree property. Okay, so after giving rotation around the grandparent, the next rotation will be in the same direction, the clockwise direction here, around the parent. So therefore this is also a zig rotation, but zig around the parent P. So after you give the zig rotation, then X comes to the top and P becomes the right child, and G stays as the right child of P. And then on this side you have the subtree A as the left subtree, and then here you have for G the subtree C and D is there, and then you have the right subtree of X becoming the left subtree of P. So again the same order, A, B, C, D is being maintained, as you can see. So the key point here to note here is that the grandparent rotation goes before the parent rotation. Okay. So grandparent rotation happens first. So you can imagine, like, if you have a large binary search tree, this kind of operation will continue to happen because you are looking through the lens of a particular node and you're seeing whether it's a left child of a right child, or it's a left child of a left child, or it's a right child of a right child, or right child of a left child. So in this way, we keep asking this question and we just keep applying these steps until there are two scenarios that are possible. So you are continuing to repeat step 1 and step 2 until you may reach the status where the concerned node, like where in this particular case the concerned node is X, that we are trying to bring it to the root. So that might have already happened. Or the second possibility is that after going through this repetition, you end up in the third case. And what is the third case? That X is a child of the root. So when it's a child of the root, so it can be left or the right child. So if it's a left child, it would look like this. So X is a left child. And you have the left subtree, right subtree. So this is the easiest case. So where you would give a clockwise rotation to bring X to the root. So this is just zig around P. And you get X at the root, and then P becomes the right child, and then C stays at the right subtree. A stays at the left subtree of X, and then B shifts from being the right subtree of X to becoming the left subtree of P. Okay, so that's about it. So these are the basic rotation that we are playing with. So let's just try to see this in action, how it would look like. So let's start with something which is sort of semi-balanced, that which is not semi-balanced, but a degenerate case of a binary search tree. So you have 15 here, you have 1 here, 0 here, 9 here, 3 here, 10 here, 2, 5, then 4, then 7, 6, then 8, then here you have 20. So this looks like quite a clumsy little binary search tree. And suppose you looked for 7 in this case. So you were doing find 7 or find the key 7. And indeed you looked for it and you found it. So you did find on the 7. So you found this node. After you found this node, then what are you going to do? So here we're going to keep asking this question: is 7 a left child of a right child? And those kind of questions. So in this case, 7 happens to be the right child of a right child. So when it's a right child of a right child, then we want to give a zig rotation. So let's be clear, when we give zig rotation, you can see what happens here. Here it was GPX, right? You get the sequence here as XPG. So this goes in the opposite order. So XPG. And the ordering of the other nodes just remains intact. So we are just going to apply the same directly. Okay. So let's draw this. So we are concerned here with this region. We are concerned with this region. And we can see that 7 is a right child of a right child. So we are applying the zig-zig rotation. So remember the zig-zig rotation, first rotation would be around the grandparent first. So we're going to give left rotation around the grandparent, which is 3. And then we will give the left rotation around the parent. So we saw we should be getting this in the reversed order, right? So it was 3, 5, 7 on this direction. You can see it changes the order and it changes the direction. So let's draw. So it will become 15, 20, 1, 0, 9, 10. So now we have to be careful. So here, what do we expect to see? So 7 will come directly here, replacing 3. And it would be in the reversed order. So 7, 5, 3. And we just maintain the order. So 2, 4, 6, 8 was the order. 2, 4, 6, 8. So that order needs to be maintained. So 2, 4, 6, 8. And I'm done with the zigzag rotation. Okay, so now I would be seeing where is 7 at this moment. So we find that the 7 is here. Now this time 7 is a left child of a right child. So when a left child of a right child, so in this case, we give this rotation first, the rotation around parent first, and then rotation around the grandparent. So let's observe what happens after giving a zigzag rotation. So you see what happens is that X is supposed to come to the root level, right? And P will become the left child and G will become the right child, right? So we try to apply the same thing in one step instead of taking the baby step of doing the parent rotation first and then the child rotation. So the region of interest here at this moment is, so 7. So we are looking at this subtree. So now we are going to apply here zigzag. So zigzag rotation will bring the 7 to the place where 1 is, right? So we'll be drawing 15, 20, and then instead of 1, we are placing 7. Okay. So at this moment, we are just looking at the subtree here. So subtree for 1 has to come first, right? So we put 0 here. Then the subtree for 7 comes. So subtree for 7 is this whole 5, 6, and then you have no, this is not right. Okay. So let's first write down how it would look like. So let's just go back here and make sure we are getting it right. So you had the configuration GPX. X comes to the root, and then P becomes the left child of X, and G becomes the right child of X. So let's first settle that. Okay. So here we had 7. So let's settle this. So first, on the left hand side, we will get the, so here we are dealing with 1, 9 as the grandparent and the parent, right? So grandparent will become the left child and parent will become the right child, right? This maintains the binary search tree invariant. And now we just place the rest of the things in order. So you have 0 here, and then you have the entire pattern of subtree from 7. So that will come here. So this is going to become, sorry, 5, and then 3. This entire subtree is just straight away coming here. 2 and 4. So we took care of this subtree. Now we take care of the subtree that is below 7. So that would be coming next. So that will become the left child. So this will become 8. And then the next subtree, which is a single node also, which is a 10. So that will come on this side. All right. So let's again pay attention to where is 7 now. So 7 is here. So this is case number 3. So it's a child of the root. So all we have to do is make one rotation in the clockwise direction. So if you make that one rotation, so this is going to be just zig rotation. So again, let's be clear on what is expected. So you can see it just X will take the position of P and P will take the position of X in the other direction. So let's do that. So you have here 7 coming to the top, 15 becoming the right child of 7. Okay. And this stays at the right child. And then on this left side, you have 1, 0, and this is 5, 3, 6, 2, 4, and so the whole subtree rooted at 9 comes here. So you have 8 and you have 10 here. So you can see the number of levels here, or the depth of the tree has reduced. So 1, 2, 3, 4. So here the depth of the tree is 4. The depth that we started off with was 1, 2, 3, 4, 5, 6. So we started with the depth of 6. So after these series of zigzag rotations, following the Splay tree convention, we reach a very effective configuration of reducing the depth. So here is a fact that we are not going to prove, but something that you can take note of, that a node initially at depth d from the access path from the root to x moves x to the final depth which is less than equal to 3 plus d by 2. So you can see, so there is a halving or reducing the depth d by half plus 3 happening at every step of the Splay operation. And this is true for any node. So, and therefore, with the Splay operations that is done, it would lead to shrinking the depth of the nodes, and as a result, it would bring the complexity with the series of operation to an average of log of n. And this is the basis for its average complexity of log of n. So let's complete the rest of the operations that we are generally interested in. So when we are looking for insertion, so when we insert, so when we insert, we are typically inserting the key k value v. So what do? We insert the new entry kv. So this step is a ordinary binary search tree step. So there is nothing new here. Then we splay the new node to the root. So how? By the series of the splay operations, a series of these zigzag operations that we discussed. Okay. What happens when you remove? So when you remove a key, a node with value key, so what is the procedure here? So an entry, a node having key k is removed from the tree. So this is removed following the algorithms that we discussed in the binary search tree, like all those 3 cases that we discussed, node having no children, a node having only one child, and a node having both the children. All the 3 cases are applicable here. So you just follow the regular binary search tree removal procedure. Okay. So key k is removed from the tree as with ordinary binary search tree. So let x be the node that is removed from the tree. So what do? You splay the parent of x. So x's parent to the root. So if you have to take an example, so you can see 2, 1, 7, 5, 8, 4, and suppose we are trying to remove 4. So this is what is getting removed. So after removal, then you splay this node. So you splay this node to the root. So which means clearly for splaying the node 5, it is a left child of a right child. So this will require zig-zag rotation. And we now know how to handle this. So 5 will come to the root. And then on the left hand side, if you have 2, right hand side, you have 7. And then you just follow the same order. So you have 1 on the left. Then you have 8 here. And that's what you would end up in. So I hope that is clear. Now, other possibility that can arise in the case of removal is that if key K is not in the tree, then what do? You splay the last node visited where the search ended. So splay is always to the root. In other words, you are using the operations as a pretext for performing splay operations. So generally the splay trees use operations. So operations here are whether we are doing a search, let's call it find, either you're doing find or remove or insert, it does not matter. Whatever operation is, you're using operations as a pretext for performing rotations, display operations or rotations. And you're doing that because now you know that by doing it sequentially, you are able to reduce the depth by half at every step. But at the end of all of these operations, as you noticed that the resulting tree is not fully balanced. I mean, fully balanced would look like this. Or look like this. So it tries to cover the entire series of levels that are possible. In other words, if you have n nodes, you will have log of n levels. So it tries to fill up those levels in a dense manner. So in other words, the splay operations are not so much worried about producing balanced binary trees, but it is just nudging in the direction of balancing and allowing us to take advantage of the semi-balanced configuration and able to achieve this order of log of n complexity. So one thing that I mentioned before, we wanted to check why rotating around grandparent is done first. So in order to understand that, let's take an example. So this is Y rotate around the grandparent first for zig zig operation. Okay. So let's say you are receiving inputs in the following sequence: 0, 1, 2, 3, 4, dot, 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 9, 10. So this is the order in which the sequence is coming. Recall that in the binary tree, okay, in the binary tree, in a binary search tree, this would have directly produced a normal sort of straight line, the linked list kind of configuration, where it would look like so, which is clearly undesirable. So now let's see what kind of structure it's going to produce when you are inserting in this order in a splay tree. So you start with 0. So you introduce 0. Then you insert 1. So when 1 comes, so first 1 will be assigned here, right? And you would be performing splay operation because you will be splaying it to the root. So it will become 1, 0. Then you insert 2. So again, we want to keep whatever is inserted at the root. So the configuration will become, so if you want to see the step, it will be 1, 0. The 2 got inserted here and it got rotated. And therefore it became 2, 1, 0. And then at this stage, when 3 comes, 3 will come here. And then it will get rotated again. So you can see at every step, it just makes it skewed completely after each splay operation. So at the end of, so it will look like this, right? So 0, 1, so 2, 1, 0. And then when you introduce 3, it would look like this. And then when you splay, it would become 3, 2, 1, 0. So it seems to not help, right? And then at the end, with the value 10 coming into picture, it would look like, so let's say 10, so 8, 7, dot, dot, dot. And then it will make again the rotation just to bring 10 to the root. So it would look like this: 8, 7, dot, 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 0. Okay. Now, when we are in this state, right, and we want to execute a find operation. So let's say find of 1. Okay. So you can see, so 1 was here. So clearly it's a left child of a left child, right? So let's see how you would go through the series of steps. So in order to appreciate this, let's just work through, if you have a smaller situation. So 4, 3, 2, 1. Okay. So you're doing the operation find of 1. And suppose I want to rotate around the parent first. So if you want to rotate around the parent first, you would first make it 4, 3, then 1. Sorry. So you are going first in this direction. So 1 and the 2 comes here, and then you're rotating around the grandparent. So sorry, we didn't do it properly. So 3, once you rotate, so 1 will come here, and then 2 will become the right child. And then it will give one more rotation, and then it becomes 4, 4, 1, 3, and 3, and then 2. This left child of 3 would become 2. The right child of 1 becomes the left child. So you will get this kind of configuration. So you can see the pattern that it is going to follow. Now, after again splaying 1 here, because we are trying to find 1, it will, you want to give one more right rotation here. So you have 4 coming here, and then the rest of the tree goes down here. So in other words, in the case where we are seeing that when you have the 0 to 10, then the configuration likely would be, after finding 1, it would be something like this. So pretty much if you had a 0 here, then you had 0 here consistently, and the 0 was here. So the configuration would look like 0, 1, 10, and then 9, 8, 7, 6, 5, 4, 3, 2. So this is the result if you have rotated parent first and then the grandparent. Let's look at the situation when we rotate the grandparent first for this, when we are doing. So now let's look at grandparent first. So we start with the same configuration, which you have 4, 3, 2, 1, 0. Okay. So here we are doing similar to the previous example. So find of 1. So our focus is on, just to be clear here, just to mark them, our focus was here. So we were splaying this 1 to the root. So finally 1 arrived here. So here also our focus is on 1. Okay, so now this time we are going to do grandparent first. So if you remember, when we are doing grandparent first, so zig operation with grandparent first results in opposite order of this. So it will be 4. So our focus is going here. So it's going to be 1, 2, 3. So 1, then 2, and then 3. And 0 was the left child. So that stays there. So after you have performed this operation, So now at this point, 1 came at this level. So again, this is the third case. So we do a zig rotation here. So 1 comes to the top, and then 4 becomes its right child. And on the left child, you have 0. And this whole thing becomes 2, followed by 3. So now if you have done this for the example of starting from 10, so if you have started from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. So starting in this configuration, if you rotate, so in the zig-zag rotation, if you rotate grandparent first before P, before the parent, as you perform the find operation on 1, okay, which means that we are splaying 1 to the root. So here also the focus is going on 1, which we are splaying. And with the rotation parent first, we reach this configuration. So now let's see what we're going to get when we are rotating around the grandparent here. So we will see that we will reach this configuration. So 1 will come to the top, and then 0, very similar to this. And then on this side, you will have 8, and then 6, so 9, 10, and you have 6, 7, 4, 5, 2, 3. So the number of levels here was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10. So the depth was equal to 10 here. And our focus is on splaying this 1. So after going through a series of grandparent first and then parent rotation, so the number of the depth that we have reached here is 1, 2, 3, 4, 5. So here the depth from 10 we have reached 5. What was the depth here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So here the depth equal to 9 if we had applied the rotation around parent first. And that is why they have established that the rotation for zig rotation means grandparent first. So this is what I wanted to at least show practically through this example, why the zig-zag scheme, the rotation around the grandparent first. So hopefully you appreciated this with the help of this example. So thank you very much.